a set of 2 more functional groups. We're going to go through the same things we've been learning in chapters 12 and 13 when it comes to learning how to name these compounds, recognize them, draw the Lewis structures, as well as the physical properties of them and different types of reactions that occur with them. So last chapter we talked about this concept of the carbonyl group, which is a C double bond to an O. But this functional group, the carbonyl group, is not distinguishable on its own. There are a lot of groups that have these. There are actually 3 groups, different functional groups that we're going to talk about that have this. Aldehydes, ketones, and the third one will be carboxylic acids, which has its own chapter that we'll discuss later on. So we're going to first be talking about aldehydes and ketones. And really the distinguishing difference between aldehydes and ketones are that aldehydes will be terminal and ketones will be internal. And so what I mean is that an aldehyde must have one of the sides of the carbon, that is the carbonyl carbon, has to be a hydrogen. And we know that if this is a hydrogen, this means this is the end of the carbon chain right here, right? Can't go on any further, which means it's going to have some sort of what we call an R group on this end, which could be a chain of 5 carbons, chain of 1 carbon. A hydrogen here would even be another acceptable aldehyde, but at least one side has to have the hydrogen. Ketones, on the other hand, are not terminal, which means the carbonyl carbon has to be attached to at least 2 carbons like it is here. And then from there, this could have various numbers of different attachments to it. So here is an example of both an aldehyde and a ketone with common names. So formaldehyde has "ide" in the last root of the word, and that kind of tells us that we're dealing with an aldehyde. And acetone, ending in "-one", is the root for ketones. So you can see here are carbonyl carbons, and here's one with an H at the end, and here's a sandwiched carbonyl carbon that is in the middle of a chain. So go ahead and answer this question. Alkenes are the only one of these so far that we have discussed that does not have a carbonyl group. So, oops, hopefully those will all go away. Don't mind any of that. Sorry about that. Aldehydes and ketones, we have quite a few of them that are very common. They also have common names to them. So oftentimes we call propanone, we often call that acetone. We don't say 2-propanone here. You can if you need to, but we don't say 2-propanone because remember ketones have to be in the middle, and so the only place the carbonyl group could be is in the center here. So we'll go through learning some naming systems here, as well as some common names for these and the different properties they have. So we'll start with naming aldehydes. Aldehydes are going to follow the same IUPAC rules that we've had for everything else. Now we're going to have a new root ending to it. So now we're going to have the root ending AL, this standing for aldehydes. So again, we're going to pick the longest carbon chain that contains the carbonyl carbon of the aldehyde group, just like we always have. And because it's terminal, we're always going to give the aldehyde, the carbonyl carbon, the number 1 numbering. So here are 2 examples where we have bromobutanol and we have 2-ethylbutanol. And in both of these cases, we're going with the understanding that this is the number 1 carbon. So this is a little easier. There's not a whole lot of guesswork with these aldehydes. So which of the following can be described as an aldehyde? This is the only one that's an aldehyde. This is a ketone-like structure. This is an ether, or actually this is an ester, we'll learn, and then this is a carboxylic acid. So we'll learn more about some of these as we get going, but this is the one that is an aldehyde because of that hydrogen. So go ahead and name these following compounds. I would encourage you to pause right here and then go back and check that you have named these correctly. So as we go through these, the first compound would be named butanol. The second compound is 3-bromobutanol, and the third compound is 2-ethylbutanol. Go ahead and name, name this compound. 3,3-dimethylbutanol. Now, we have a slightly different system that we have to deal with when we're dealing with a ketone. First thing is that the root ending now will be -one, O-N-E, to represent ketones. The carbonyl carbon, we want it to be the lowest number possible. It won't necessarily always be the number 1 carbon, like in aldehydes, but you want to give it the lowest number possible. So here's an example in a straight chain, and here's an example in a cyclical compound. So yes, when we have a carbonyl group like this in a cyclical compound, this would be considered a ketone, which is a little weird. So which of the following is a ketone? 2 is a ketone. Give the following IUPAC names for these ketones. So I would encourage you to pause the video here and go through and name these compounds. So the first compound is propanone, and like we talked about earlier, you could put 2-propanone, but it's understood that the carbonyl has to be in the center carbon, so it's a little bit excessive to put the 2 in there. So we don't have to call out the number 2. Next would be 3-methyl-2-pentanone. And lastly, we have 2-methyl-cyclohexanone, which the following is not an accepted name for this compound. And so this would be the propene, because we have no alkene group here. There's a double bond, but that double bond is part of the carbonyl. It's not part of the carbon chain, which would make it an alkene. So when we look at the physical properties of aldehydes and ketones, we have to be very, very important about what we're talking about here. The carbonyl group is not a OH bond. It's a C-double-O bond. Now there is an H here, but that H is not directly attached to this O. So in both of these cases, there's no hydrogen bonding occurring here. Because of this, the boiling points of aldehydes and ketones are going to be lower than alcohols of similar weights. But they're still polar, so they're going to have dipole-dipole interactions, which will give them higher boiling points than alkanes because of that those dipole-dipole interactions, that polarity to them. So here's our general chart that we keep growing in terms of all the different functional groups and their boiling points and such. So aldehydes and ketones, this is what I'm gonna repeat this a few times because it is a little tricky, but it's an important distinction. Aldehydes and ketones, they cannot do hydrogen bonding with themselves. So if I have this aldehyde and I had the same exact aldehyde again, like 2 molecules of the same aldehyde, they would not be able to hydrogen bond with each other because there's no OH bond. However, they are able, the carbonyl bond is able to hydrogen bond with water molecules, okay? So aldehydes and ketones cannot make hydrogen bonds with themselves, with other molecules of the same compound. However, they can make hydrogen bonds with water, which makes them fairly soluble in water. Go ahead and answer this question. The correct answer here would be butanol. All of these are true. So we're going to start talking about some chemical reactions that occur. How do we get an aldehyde? How do we get a ketone? So if you remember from our previous chapter, we talked about how we took primary and secondary alcohols, and when they were exposed to oxidizing agents, they became aldehydes and they became ketones. So this is how we make an aldehyde or a ketone, from the oxidation of either a primary alcohol to make the aldehyde or a secondary alcohol to make the ketone. Remember, aldehydes can be further oxidized into carboxylic acids. Ketones, on the other hand, cannot. Aldehydes are the functional group that can be further oxidized to carboxylic acids. So the difference in reactivity towards the oxidation is the main reason why aldehydes and ketones are in separate families. Because aldehydes can go and further oxidize into carboxylic acids, that's why they're in their own group and not kind of lumped in with the ketones. So there are a couple different reactions using different dyes, essentially, these reagents, to kind of identify if we're going to have oxidation occur or how effective oxidation would be. Tollin's agent and Benedict's agent, these are both mild oxidizing solutions that will essentially have materials change color when they're oxidized. It's a test we can do in a lab to identify oxidizing or reducing sugars. So in this case, something that could be oxidized. Ketones, because they can't go through this further oxidation, do not react with these reagents. So if you had two vials and you were told one was an aldehyde and one was a ketone, you could use these, either the Tollin's reagent or the Benedict's reagent, to determine which one was the aldehyde. Which of the following compounds would you start with if you wanted to form 3-pentanone through an oxidation reaction? So I would encourage you to pause the video here, go through, draw the compound 3-pentanone, and then figure out what would you have to have as a starting material for that. Think about what makes a ketone. What kind of alcohol gets oxidized to make a ketone? That might be a good hint for you. So in this case, 3-pentanol would be the best option. If we reduced a ketone, what would we get? So we know we take something and we oxidize it and it becomes a ketone. If I take a ketone and I reduce it, do the opposite reaction to it, what would I get? I would get a secondary alcohol. So, similar to what we had seen in alkenes, we can do addition reactions. So we can add hydrogen to our carbonyl group, and when we do that, we get alcohols. Right? So this is how we go through the reduction process, is by hydrating it, or hydrogenating it. So if I have an aldehyde and I break apart my carbonyl, I add hydrogen to it, I now have a primary alcohol. If I take my ketone and do the same thing, I will end up with a secondary alcohol. What would be the product of the following reaction? It would be an alcohol. We would end up with an OH group here, and an H group down here. So this would be a cyclohexanol. I'm going to briefly talk about hemiacetyl groups and acetyl groups and hemiketal groups and ketals. Just briefly, we'll see more of these when we get into our biochemistry section. I just like to expose you to them now. But basically what can happen is when aldehydes react with alcohols, we end up with something that kind of looks like this. And then if they react further, we get something that looks like this. So we get a double ester, essentially, where we go from alcohol ester, or alcohol ether to a double ether. And here's an example of these types of reactions that occur. Like I said, this will be more common, and we'll see this when we get to our biochemistry section. So this is what happens with the acetyl groups, which come from the aldehydes. We can also have this happen with the ketones. So hemiacetyl groups are formed when aldehydes react with what functional group? Alcohols. Ketone reactions can go through the same things. We call them hemiketals or ketals. And again, here's that alcohol ether or the double ether version of it, with some examples for you to look at. Like I said, we will deal more with this when we get to our biochemistry section. So I want you to go ahead right now and kind of just visualize these and identify whether these would be hemiacetyl, hemiketal, acetyl, or ketal groups. So you can go through and identify each of those. We can also have this happen in a cyclic system, and this is what we'll see in our biochemistry exploration. This is where we start seeing these kind of alcohol sugars. We start having these carbohydrates that will cyclize on themselves, and these are where we will get those hemi structures. So which of the following is a cyclic hemiacetyl, hemiketal, or acetyl or ketal group? Again, go through and make sure that you are able to identify each as either the hemi version or the acetyl or ketal group. So these acetals and ketals, these guys right here, where we have the double ether, are capable of undergoing hydrolysis. And when we do that, we go back from the acetal to the aldehyde, or the ketal to the ketone, and the alcohol that it reacted with. So here's an example with a ketal, right? When we hydrolyze it, when we add water to it, when we hydrate it, what we end up doing is getting our ketone back, as well as the oxygens that were used to make it. So here's our roadmap of the different kinds of reactions that can undergo, or aldehydes and ketones can undergo. Again, I will leave this up for you. I'm not going to go into much detail. We won't be asking you about it. Some students like to see the actual process, how these different mechanisms work. If you go on to take an actual full organic class, you will have to learn how to do these. So I would encourage you to pause right here and and go through and try and predict what you think the best product would be for this reaction. So we have this group here, identify what it is, and this group here, identify what this is. When this adds to this, something special is going to happen, right? We have a cyclic hemi-ketal. If we add another alcohol to it, which this is, we're going to get the ketal version of it, plus some water. So we already talked about this a little bit, but there are some important aldehydes and ketones that are used in our day-to-day lives, as well as for medical purposes. So the first one would be formaldehyde. It's the simplest aldehyde we can make. It's a gas at room temperature, and for a long time it was used as like a sterilizing agent, an embalming fluid. So we don't actually use this anymore for like any sort of live dissections, or not live dissections, but dissections of preserved tissue and things like that, because it is also known to be carcinogenic. So we do use other reagents these days as a embalming fluid. Acetone is another very popular solvent that we use across the board in a lot of different applications. Probably the one that most people have the most experience with would be nail polish remover. Oftentimes has acetone in it, and that's a ketone. We do have bigger, more naturally occurring aldehydes and ketones. For example, a lot of the sex hormones in the human body are ketones. So as you can see here, progesterone, testosterone, these are ketones. This actually has a double ketone on it. So again, cinnamaldehyde, this is used in like Big Red Gum and what is it, Fireball, the alcohol, to give things that cinnamon flavor. We also have things like citral, which is like a lemon flavoring, camphor, which is kind of like a medicinal type flavor, methanone, which is part of like a peppermint flavoring. So as you can see, these aldehydes and ketones are very, very popular in kind of flavors and scents that we use in a lot of foods and candies and things like that. So this ends our chapter 14 slides. I encourage you to do the reading in the text as well as the homework, and check out the extra help section that we have for Unit 3 on Canvas.